So we're going to work on a problem here on this session. So the problem is right here. It's a statics equilibrium problem. So if you go into Moodle, it's right there. It's called the 2D Equilibrium Project. Okay, right there. It's under the homework downloads in Moodle. I've got extra copies if you want to pick one up in class too. But this is what we're working on today. So what we've got here is a bracket, and the thing has a pin joint here at point B, and then it has a load at point C, and then it's got a roller here at A on an inclined ramp. And what we've got here is the pin joint can withstand a maximum load of 3,000 newtons. Okay, that's given. So what we'd like to know is, given this bracket, what the maximum force P can be. So what's the maximum force you can apply at P, a vertical force at P, before you hit 3,000 newtons for the total force at the pin joint at B? All right, so the first thing to do here is to make this sketch into a free body diagram. So why don't you go ahead and do that. Pause the recording and get your best clean free body diagram you can get from that sketch. So what you want to do with a free body diagram is break it up into X and Y dimensions between the places where the forces are applied, and then show the forces on the object. So you want to get the cleanest, simplest free body diagram you can for that, and show the forces on it, and then you want the X and Y dimensions shown. So why don't you pause the recording, and I will too, and get yourself a free body diagram drawn, and then you can start the recording up again, and we'll have a look at the free body diagram. Okay, so I'll pause here. All right, so hopefully you've got yourself a free body diagram drawn. So let's have a look here and see what it should look like. So what we want to do is work with the geometry up here with this loop, and kind of basically cut that off is what you want to do. So you're going to want to come up with 3 dimensions basically. You've got this one here. This 0.9 I should have specified, but it goes up to there where the curve starts. So you're going to want to get a dimension here. The 0.4 you've already got, and then you also want to get a dimension there. That's really what you want. So you want to do that because you want nice clean XY dimensions between the 3 places where the forces are applied, A, B, and C. So in essence, what you want to do is figure out that geometry of the loop and then just cut it out. You don't really want to deal with the loop because there's no loads up here that are applied. So there's no reason to include that in your free body diagram. What you want to do is just turn it into a simple L-shaped bracket with the dimensions on it, okay? So let's have a look at what we got here. So there's what we get for the bracket, okay? So you've got the load P, of course, is on there. That's the one you're trying to solve for, right there. And then you have the 2 loads for the pin joint at B. And then you've got an extension out from there to that vertical part of the bracket. Well, that turns out to be 0.3 meters when you work that out. And then downward to A from that intersection point is 0.6 meters. So there's your free body diagram, okay? Now the next thing we're going to do here with this is try and figure this out. So you want to know how large of a load you can apply at P until the total load at B equals 3,000 newtons. All right, so what I would suggest you do there is write up equilibrium equations as you normally would. Now you've got a lot more unknowns on this than you might be used to, but just go ahead and write up equilibrium equations, and your goal in doing this is to get relationships between the different unknowns that you can then work with. All right, so why don't you give that a bit of a run here, and then you can check back in after you've got something. I'll pause the recording again. All right, so hopefully you've got some equations written up. Now, the one thing that's going to complicate this one a little bit, make it a bit more complicated than the other ones you've worked on, is the pin joint right there, because you know the total force in the pin joint is 3,000. Okay, now the problem is you've got both an X and Y component for the pin joint, and that's going to complicate things a bit. Now I would suggest that you kind of go with a sum of MB here. That will allow you to relate the load at P to the reaction at A. You're going to need to dimension that reaction at A with the angle, that angle that I'm showing right over here. You're going to need to get that filled in. Okay, and then so you're going to do a moment about B. I would probably do a sum of Fx and a sum of Fy. And that's going to get you relationships between these different forces. Now, the one tricky thing on this is the fact that RBX and RBY are perpendicular to one another, of course, so you can't just add them up and get a total of 3,000. You're going to have to use the theorem of Pythagoras. And that's going to make working with multiple equations and multiple unknowns a little bit complicated. But that's the way to do that. Now, there's a few ways to solve for that. And why don't you pause the recording again and see, work on that a little bit more. And then when you feel you've got some idea of how to approach it, we'll talk a little bit more about how to approach it here. All right, now, once you've kind of taken an approach on this, you might run into the fact that, again, this isn't quite as simple as the ones we've been working on so far, just due to the number of unknowns and the difficulty in relating RBY to RBX. It's just theorem of Pythagoras, but all the same, it makes kind of a linear systems of equations difficult to work with. Now, there are some ways around this. One way I just want to point out to you, now you don't have to do it this way, but it's just something I just want to point out, is probably in a lot of the classes you've had so far, you're interested in exact, perfect solutions. Now, in engineering, you're not quite constrained that way. If you can get close with an engineering solution, quite often that's good enough. You don't have to get a perfect number for things as you might in, let's say, a pure mathematics class or something like that. So that leads us to another way of solving problems. And what we're gonna do here is kind of link these equations we can develop together until they lead us to the answer. So here we go. I've got a spreadsheet set up, the ramp angle, and I've got some other stuff that helps me to determine the components of the reaction at A. And then I've got the load that I can plug into this spreadsheet. Then I'm going to walk that through, because if I know the load, I can use that moment of B equation and solve for RA. If I know RA, I can find RBX. And I can also, if I know A and P, I can find RBY. So if I kind of start with an assumed value of P, I can determine all these things. And once I know RBX and RBY, I can find RB. And I can link those steps together in a spreadsheet because they're sequential. They all follow one after the other. So what I can do then, if I don't need a perfect exact answer, is I can plug in a value of P. And I put in 200 newtons this time. And when I did that, I worked through RA, 142.9, RBX 71.45, RBY negative 323.76, and that gets me a total RB of 331.55. Well, I can go all the way up to 3,000 with RB, so I don't think P equaling 200 is big enough. I think it's too small. I can put in a larger value of P, say 3,000. Okay, when I do that, see, RB comes out to be 49.73. All right, and so once I build that spreadsheet, I can just keep entering in different values of P in until I get RB sufficiently close to the total answer of 3,000 that I want it to be, okay? So this is just another way to solve problems. It's kind of a guess and check method. The formal name for this is numerical analysis. But when you have a spreadsheet, you can do it this way. You don't have to solve it perfectly. You can just link together the equations as you work through the problem, put in things that you might think P might be, and then just see what comes out. And if you shoot high and low like I just did, now you know the answer is somewhere between 200 and 3,000. You can start to just put in different numbers until you get the answer you're after, which is a total RB of 3,000. Okay, so I just want to show this to you. Now, you don't have to do that problem this way. There's other ways to do it. But this is a good thing to know about because it's a whole other way of solving problems and can really break through some very difficult mathematical type relationships. If you just kind of put the things together and just sequentially work the equations out, you can just put in inputs till you get the proper output, the proper answer, and then you're good to go. All right, so I just thought I'd point that out. Now, we don't have school on Monday. I think this problem will be one of the homework problems that are due on Wednesday. So I just thought I'd start with that and get you going with that one. Okay, so that's all we did today. So we'll call it good.